Hello, you are welcome back. Alright, so in this video, we're going to be discussing elasticity. Alright, so what is elasticity? Now, elasticity is the ability of a material to return to its original size or shape after being deformed. Okay, that ability of a material to regain its original shape or size after it is being deformed. Now let me illustrate elasticity using this simple diagram. Here is a material that is pulled sideways by two forces, two equal and opposite forces. All right, now if this particular material actually uh, is being pulled by these forces, then it will extend a bit. Okay, due to the effect of these two forces, there's going to be a, a slight extension. Okay, uh, increase. Of course, extension is an increase in length, which we okay, which of course is delta L. All right, we're going to have a small increase in length, which of I will all right call delta L. Okay, so let me do that. So here we go. So a slight extension delta L. Now once this pulling force is being removed, what happened? The material returned to its original size or shape. Such phenomenon is what is referred to as elasticity. Alright, so please take note of that. So according to Hooke's law of elasticity, we state that provided that the elastic limit is not exceeded, the applied force, all right, in this case, which is P, the applied force in this case, which is P, is directly proportional to the extension, which of course is delta L. So invariably now, if I replace the proportional side by an equal to after, I will introduce a constant K delta L. So this K now is actually a constant, okay, known as an elastic constant. Elastic constant. Now, as we progress, you will discover that this K will have different definition, but from what we have, all right, from this simple Hooke's law, if I make K the subject of formula, K is going to be equal to the pulling force, then divided by um, delta L. All right, force is measured in Newton, then change in length is measured in meter. So that means the elastic constant here is Newton per meter. All right, so let's proceed. Let's look at a situation, and by the way, delta L is actually the increase in length, which of course is final length, okay, uh, L2 minus the original length, L1. All right, so let's look at some simple example. Now, let's say we have a material whose length, all right, originally is whose original length L1 is equal to 2 meter. Okay, so if this material is actually being pulled by a force to a length of 2.02 meter, and the force that is actually the force pulling is equal to let's say 50 kilonewton. Then the question is, what is the elastic constant of this material? All right. From what we already have, we know that the elastic constant is equal to the pulling force divided by delta L, which of course is going to be equal to L2 minus L1. So this is 50 kilonewton, which of course is 50,000 Newton, divided by 2 minus 2 point, the final length is 2.02 minus 2, which of course is 5,000 kilonewton. 50,000, all right. Okay, 50,000 Newton, then of course divided by 0.02. So if we do this, okay, we'll end up having okay, all right, let me clean up all this. Okay, so if we do this, of course, the 50,000 right here is 5 times 10 raised to the power of 4. Then the 2 is 2 times 10 raised to the power of minus 2. So this here is going to be 2.5 times 10 raised to the power of 6 Newton per meter. Alright, so I hope that is well understood. Okay. So now we are going to talk about other elastic constants. Apart from this, the one that we got from Hooke's law, we are going to discuss other elastic constants. Alright. So before we talk about other elastic constants, let's look at some important phenomena. Let's talk about tensile stress. Okay. Now, tensile stress, by the symbol is sigma. The symbol of tensile stress is sigma. Is equal to the pulling force per unit area. The pulling force per unit area. So invariably, the SI unit of tensile stress, okay, is going to be the unit of force all over the unit of area. Cross-sectional area is Newton, that is meter square. We have, so the SI unit of tensile stress is Newton per meter square. So please take note of this. All right. They will now have the tensile strength. Every stress force per unit area on a material will produce a strength. And how do we define the strength? The strength that is being produced by stress, okay, is the strength which of course we use small letter e to represent, is given as the extension produced per unit length of the material. The extension per unit length. So here, this does not have any unit. The reason being that extension is measured in meter, length is measured in meter, meter cancels meter, so there is no unit. All right. Okay, so now that will bring us to another definition of elastic constant known as Young modulus. Young modulus of elasticity is another constant. Okay, So we are going to look at another constant known as the Young modulus. Young modulus of elasticity. The symbol of Young modulus is capital letter E. Okay, so we now have that Young modulus, right, is going to be equal to the stress, the ratio of the stress divided by the strength. Ratio of the stress divided by the strength. That is going to be the ratio of force per unit area divided by delta L all over L. So the unit, the SI unit, is going to be Newton per meter square. Since strength does not have any unit, so the SI unit of your modulus will take the same unit as tensile stress. I hope that is well understood. Okay. Can we look at some example? Yes, we can. Example. Okay. Let's say we have a material whose length is 2 meters. Okay. That is actually extended by 0.5 meter by the application of a force of 20 kilonewton. Okay. Now, if the cross-sectional area of the material is 2 meters square, the question is, what is the modulus, the Young modulus of elasticity? Solution. Okay. So from what we have here, so we can have that the Young modulus capital letter E is equal to the tensile stress all over tensile strength. So we can take it one after the other. Sigma being the tensile stress is equal to the pulling force all over area. Okay, so there's gonna be 20 kilonewton. That's gonna be 20,000 newton divided by the area, which is 2 meters square. So if we divide this, if we divide 20,000 by 2, I'm gonna have 10,000. So that's gonna be 10,000 newton per meter square. All right. Then the next, okay. We are going to look at okay. So we are going to evaluate the tensile strength, which of course is the extension per unit length. Extension from the question is 0.5 meter. Then the length of the material is 2 meters. Okay. So this of course should give us 0.25 meter. So applying the formula, applying all the parameters into this, so our Young modulus of elasticity is going to be equal to the tensile stress, which of course is 10,000, divided by the strength, which of course is 0.25. All right. So let's do this. Let me perform this calculation with a calculator. All right, here we go. 10,000 divided by 0.25. 40,000. So our Young modulus of elasticity is 40,000 Newton per meter square, or you can write it in a standard form. Okay, it can be written in a standard form, that is 4 times 10 raised to the power 5 Newton per meter square. I hope that is well understood. Can we proceed? All right, let's proceed. Let's look at also some other important concepts. So this time around, let's look at what is known as shear stress. Okay. Shear stress. How do we define shear stress? Now this time around, when you have, okay, a force that is tangential to a material that try to deform the material in an angular form. For example, this is a force that is tangential. Okay, one force. A tangential force is a force that is pulling on the material at the surface, parallel to the surface. Okay, this is where this force is. Let's say this is where the force is, a tangential force. Let me call it P. Then another force here, also parallel to the surface. So what this is going to happen is, what's going to happen to this material? There's going to be some angular deformation. So there's going to be some angular deformation by this tangential force. So there's going to be a angular deformation, which is delta L. Then that will happen per unit depth or height of the material. So this is where we now define our shear stress. Shear stress by the symbol tau, okay, is equal to the pulling force, okay, or the shear force, then divided by, okay, divided by the area, okay, of the material. So please take note of that. It's still the same, but the difference is that this time around the force is not a tensile force that is pulling the material apart, but the force is actually tangential to the material. Okay, but okay, of course, the SI unit still remain the same. We have Newton per meter square. Okay, so with what we have so far, so good. We can also define shear strength, because every stress will produce an equivalent strength. A shear stress on a material will produce a shear strength. What is the shear strength? Okay, so we are looking at the change, the angular deformation, all right, per unit height of this material or per unit depth. Okay, so that simply means that the shear strength, okay, so the shear strength, let me use EX to represent that, is going to be equal to the change in length, then per unit height, all over H. All right, this one now is not per unit length, but per unit depth of the material, delta L all over H. So this is shear strength, and of course, as usual, there is no unit. So this doesn't have any unit. Okay, so that is it for this video. We are going to look at example to all this. All right, we're going to solve some question before we now continue. All right, so see you in the next video. Thank you very much.